And offset. And shadows. And hide it. Right. Now, I can still control it. Excellent.
Are you chairing your own session?
I am chairing my own session.
Okay. Yeah.
You're going to introduce yourself then?
Yes, I absolutely will. Hello, everyone. My name is Henrik, and I would like to present this talk given by Henrik. So the title of this talk is by far my favorite title for all the talks I've given. Can you hear me on Zoom, by the way? Yes, they can. Excellent.
Yes.
Yes.
Okay, so the title is Counting is Hard. So this is joint work with my supervisor, who could unfortunately not be here today because he is in Switzerland. I know, it's a shame. So this talk is based, I would say I'm presenting a small subset of a journal paper that we are currently writing. And this will be submitted to TCAD, so Transactions on Computer-Aided Design. But then we have to submit it under a different title because electrical engineers and fun titles don't really go together, unfortunately. Yes. So this talk, in a nutshell, is about three things. So the motivation for our work is a problem of computing signal probabilities exactly. So we will not talk that much about that, but that's the motivation. But computationally, this is a very, very hard problem. It is as hard as the problem of model counting, which we will talk about as well. And the way we tackle this problem is using symbolic simulation, BDD-based symbolic simulation. And the tricky thing then is how to constrain this symbolic simulation so that you only run the things you want. But we will get to that. And of course, during a talk, you can talk about all the engineering behind the scenes that you cannot write about in the paper. So I will spend some time on that. So signal probability in a single slide. This is our motivation and application. Simply put, it is the probability that a node inside a circuit has the logical value 1 over time. So this is useful in many fields. For example, in power estimation, most of the power in a circuit is consumed by switching, and you can express this in terms of signal probabilities. So the tricky part in power estimation, the factor you don't know is this switching. How much switching do you have? But you can express that in terms of signal probabilities. And if it's exact, you get more exact estimates. It's also useful in reliability analysis. Here you're looking for faults in a circuit, so you may have nodes stuck at 0 or 1, or you may have delay issues. So you lose values because your flip-flops are not fast enough, usually. And what you're trying to do here, before you build the circuit, when you design it, you want to detect these critical nodes, because a single fault should not destroy the entire circuit. And you can, if you detect these critical nodes, then you can use things like what's it called? Redundancy. You make redundant nodes, and then you take the majority of 3, for example. Then you need 2 issues. You need 2 faults.
Is it okay to ask questions, or?
Yeah, go ahead.
So I don't understand the probability of faults in a circuit. How does it relate to signal probability?
You can use signal probabilities to. This is not my field, but you can use them in the critical nodes are the ones that have a lot of activity, and you can use signal probability to find that.
Okay,
and you can detect, for example, if you have a fault at this node, how much does it propagate?
Okay,
I think so. As far as I understood,
so the signal probability doesn't predict the probability that you get stuck at 0 or stuck at 1. It's how the signal probability can be used to analyze if that happens. How bad is it?
Yeah, for example.
Okay.
I think so. This is not my field. This is just what I've been trying to read out from the papers of other fields, which is tricky.
So I have a question about signal probabilities as well. The probability that a node might carry the value 1
yes.
could depend on the history. previous state of the circuit.
Yes,
Is that taken into account here, or are we talking about an average over all time?
we're talking about an average of all time.
Okay.
And the final motivation that I found was in test pattern generation. Here we are really looking for the same problems as in reliability, but now we have the designed circuit. So now we want to find inputs that we run through the circuit, and then we look at the outputs, and those are the only ones we can actually observe. And we want to create vectors that such that we find these issues. And there are many faults where if you just do this uniformly, randomly, you will not find the fault. You need to bias the distribution. And you can use signal probability to do this in a more efficient way. Okay, no more motivation. So even in very, very simple combinational settings, even if you have no state at all, exact signal probabilities is a very, very challenging problem from a computational perspective, as hard as model counting, which again, we will get to. So most related work, they rely on approximations. But in this work, we will see how far we can get with exact solutions. So for this talk, we will consider only the simplest of settings: combinational, ideal, zero delay, combinational circuits with idealized zero delay gates. So every node is just a Boolean function over the input bits.
So can I, even though this your assumption is zero delay, you don't have zero delay. You get all these.
You will get transient values,
right?
That may depend on.
You get switchings there. Right. And is that something you consider in your paper?
Our methods can definitely be extended to that without. It will not complicate things that much.
You model it by actually putting this delay.
We can put explicit delays, and nothing will change. But
it will be much more expensive.
It will be more expensive, definitely. Yes.
Okay. Sorry.
Yes. And right. So since the value of every node is a function of the input bits, the signal probabilities will be a function of the distribution over the input bits. And we will consider a very particular distribution, which is the constrained uniform distribution. So we have a constraint over the input bits, and then everything, the set of vectors that satisfies this constraint, we want to do that. We want to be uniform over them, and then everything else will not happen. So the probability of generating a vector that satisfies this constraint is 1 over the number of vectors that satisfies the constraint, and 0 otherwise. And then finding the number of vectors that satisfies the constraint is a model counting problem in itself. So let's look at the absolutely most naive way you can do this. So you have 2 input bits, N1 and N2, and you have some bits in the middle, but let's look at the signal probability of the last bit. So as usual, you draw up your truth table, and then you run all of the vectors one after another, and we fill up our truth table. 0, 0 maps to 1. 0, 1 maps to also 1. 1, 0 is 0, and 1, 1 is 1. So here the signal probability of the last bit is just 3 over 4. Simple enough. And now if we have an input constraint here, let's say the input constraint A or B, what essentially happens is we remove the rows that do not satisfy the constraint. So here we have removed the 0, 0 row, and now we have 2 out of 3, so 66%. And fun fact, when I made this slide, I wrote 33%, because counting is hard. So when you have an unconstrained signal probability, you have the model count over 2 to the n. And when you have a constraint, what you do is you take the function for the node over the input bits, you conjoin that with a constraint, you take the model count of that, and then you divide by the model count of the constraint. Yes. Of course, this naive exhaustive search, it does not scale. So, because of course we have an exponential number of input vectors to check here. And finding a single solution to each bit, that is the SAT problem in itself. So model counting is even harder. It is in the complexity class of sharp P complete, which I had never heard of before starting to work with this. But of course, we know that formal verification tools, they are great for covering large search spaces. So with symbolic simulation, you can just put a Boolean variable on each of the input bits, and then you propagate that. And for this, it turns out that BDDs are great. So here we have the BDD for the final node here, which is not A or B. Not A or B, they match, yes. So model counting with BDDs uses a bottom-up recursive algorithm. So you annotate each edge with its result, like this. Here you have 0 solutions because it's 0. There you will find 1 solution, and then you take the sum of the child edges. So 1 plus 0 is 1, yes. And for the final one, it's actually not 1, it's 2, because it doesn't matter what B is. B is a free variable. So here you have 2 solutions. And the answer is 3, which is the same as we got before. That's good. And the thing that makes this work is because you have a memoized implementation. So you cache and look up all of these intermediate results. And as a result, you get the complexity in the order of number of nodes in the BDD. So a simple BDD method for computing signal probabilities exactly is to symbolically simulate the circuit with BDDs, completely unconstrained. And this will get you each node value as a function of the input bits. And then you loop over each node, and you use the formula from before. You conjoin with a constraint, take the model count of that, and divide by the model count of the constraint. Yes. The problem with this is that unconstrained symbolic simulation, this will lead to a lot of redundant work. So when you take this conjunction, you will throw away a lot of the work you have been doing. So especially if the constraint is very tight, so very, very few vectors actually satisfies the constraint, then almost everything you're doing is completely wasted. And also for some circuits, such as for multipliers, you cannot run unconstrained BDD symbolic simulation because it is inherently exponential. So can we then incorporate this constraint into the symbolic simulation itself? And the go-to tool for this, for BDDs, is parametric substitution. So here is parametric substitution in a single slide. So you have n input bits. You have B is a bit, and the constraint is a function from n bits to a single bit, and this has to be satisfiable. You say that S is the subset that satisfies this C. And then param, the parametric substitution is like a higher order function that takes this constraint, and the result is something that maps into this satisfying set. And then you have 2 properties here. You have sumness, so everything that comes out of this will satisfy C, which you kind of get this through the type annotation here. But also completeness. So there will always be a value that you plug in that will give you every value of C. So you can get, yes, the image of param C is S. And I like to think of this as it's sound because we can generate only the good vectors. We can only generate things that satisfy C. And it's complete because we can generate all of them. So we can generate all the vectors that satisfy C. Yes.
Yes. So I don't understand.
No.
So C is a constraint.
C is a constraint of the input.
What is param C? I don't understand that.
So S is a high order function
that takes
any
any vector. and returns something in S, or what?
Yeah, it fixes the input. So it takes any vector and then it gives you an input that actually satisfies C.
But you could just return always one element.
Then it wouldn't be complete.
Then it's not complete.
Yeah, but okay. So I thought completeness was derived from those things, but
No.
No, these are properties that is guaranteed.
So parametric isn't guaranteed to be the identity on elements of S. We'll get to that.
Okay, so these are requirements on parameters.
These are things that are guaranteed.
Guarantee. Well, we require them from parameters.
To design a function. That's right.
We are assigning a higher order function that takes in a function,
Yeah.
which is then a mapping into the set that satisfies the
So
constraint.
it's like saying if you have orderedness of a list as a precondition, that's a condition you can check.
Yeah.
And you can reject your inputs when they're not ordered, but you can also have a function sort that takes any input and it turns it into something that satisfies the precondition.
Okay. Yes.
And
And that is para.
That's what parent is.
And that's the function we want to find now, or is it? Or
Yeah, I guess.
So
There's more requirements to parent, I guess, than these on the slide.
So a general parametric substitution only has these two parts.
these two.
These soundness and completeness. These are the requirements of a general param.
Okay.
So the image of param C is the same set as S.
Okay.
So
So
it's very simple.
soundness and completeness are requirements, not
These are requirements.
Okay.
Yeah.
So I thought you proved them, or you could prove them for any.
You can, but yes, these are required. Basically.
Okay.
So a very simple param C, which is take an input, check if C holds. If it does, return it. And if it doesn't, return some kind of always the same input where it doesn't hold anyway. That would be very simple. param C.
That is a parametric.
Yeah.
Okay. I think I saw something in the chat.
Yeah, I just wanted to ask a question or comment. So I assume that, especially when you have rather sort of heavy constraints, I mean sparse things, then you would like to have another n. So you have you want to generate 128 bit vectors out of 32 million.
Yes.
And you don't
yes.
want more than 7 bits.
No.
input For that.
You can have a different n for the two sets, but we don't consider this in this talk.
Okay.
Yes, you're absolutely right. So here's a very simple example of a parametric substitution, the simplest I could come up with. The constraint is just A or B, and there is a single vector that does not satisfy this, which is 0, 0. And param C comes back and say, well, your A should be replaced with A, your B should be replaced with B or not A. And if we draw the truth table for this, we see that 0, 0 maps to 0, 1. Nice. And then everything else maps to itself. So this is sound and complete. But as you see, everything else maps to itself. So it does this hold in general. So yes, this identity property, I accidentally discovered this during this work. And it does, well, it's quite obvious. For everything that satisfies it, it maps to itself. And here we are talking about the built-in param in BOS2. We're not talking about the general parametric substitution. And now we have a proof for this. But let's explore how we got there. So let's go back in time to when I was tinkering about on my computer and then suspecting that this holds. So can we then quickly check for counterexamples? So I come up with this completely original idea for testing software. So you you generate a BDD and you check if that satisfies the property. And if it does, you just keep going until you run out of patience and then you return. Or if you find something that does not satisfy it, then you try to find a smaller counterexample and you return. So I wrote this was check main, and indeed it takes a generator that takes an integer and returns a generic A, and then you have a property that takes the A and returns a bool. and a bunch of optional stuff as well. And I would like to say here that optional arguments, they are new in BOS2, and they are great. I cannot stop using them everywhere. My code looks horrible. But it would look even worse if I didn't use optional arguments. And so I defined my property, my generator, which is gen BDD over size. I will not show you gen BDD because it's extremely ugly. And you have a property that I will show you in a second, but it's quite obvious. The only thing here is that if it is the constant function false, then the property doesn't, then it's not satisfiable. The constraint is not satisfiable. So we don't care. And it's nice to be able, it's also nice to be able to print things. And then we just run this. And the actual check identity is we just enumerate all of the solutions, and then we check them one by one if they actually satisfy the constraint that satisfies the property. But this is not that important. So I made this GIF. This is in the most verbose mode I can come up with, and it is beautiful. It is testing so many things, and it's not finding anything. It's not finding any conflict.
Wait, your GIF is looping, isn't it?
Yeah, the GIF is
Okay.
I would just like to stop here for a moment.
There's a comment in the chat.
Can you read the comment aloud, please?
Henrik has seen the light.
I have. Is it Roberto who wrote it?
Yes.
Yeah, it is. Okay, so this is nice, but we would like to also have a proof. And I will show you a proof sketch. So what we do is we define a function p mathematically with the same semantics as the param function. And then we prove by induction that p satisfies this identity.
So this is a particular param function we're talking about.
This is the built-in param in BOS2.
There's a built-in param in BOS2.
The built-in parametric substitution function in BOS2.
I see.
No, that is what we're proving.
Okay.
Yes. So this p function here, you don't have to read everything, but you have a p, which takes in an f, which is a satisfiable Boolean function. So this is our constraint. And then as a lambda, it takes in this vector that we want to map. And if the vector is empty, then we return an empty vector. So trivially, that is our induction base case. And then for the inductive step, we just look at each of these case by case. And it falls out quite nicely that P(f) of V is V. And all of them more or less look like this, all of the cases. Nice and clean. It only took 8 attempts to get it right.
So Henrik,
Yeah.
Well, I mentioned a very simple param function before.
Yes.
It just says, give me an input, I check if it holds. If it does, I return it. Otherwise, I return a random input for which it holds.
That is also an identity.
Right. But why aren't you using that one? What properties does this function have that you like better than the one I just told you?
Nothing that I'm talking about here, but we want to create as small BDD expressions as possible. And let's see if I can. So the param in BOS2 will try to generate as many of these as it can. Just A to A, B to B, do. And then it piles up all of the difficulties to the last one, more or less. And that will give you small and nice BDD expressions. Is what I've understood from Carl.
Okay. Because the one I suggested would have C in every input.
Yes, I've also tried that. It works sometimes, but yes.
Okay.
As per my previous response.
Well, that makes sense. Yeah.
Good. So why identity param matters? So using this identity property, we can just we do param over the inputs. We run the symbolic simulation. Now it is constrained, and now we can just take whatever value for each node and use the same formula again. We cannot do this if we don't have the identity property, which is quite easy. it's easy to show that this will give you the right result. So why it matters? Well, if you have very tight constraints, like I said before, like multipliers, they are inherently exponential in their BDD size. You cannot run them unconstrained. It's not going to happen. And then also, I made these slides yesterday. They might, we'll see if they work. Floating point addition. So a floating point number consists of an exponent and a mantissa and a sign bit. We don't care about the sign. So when adding two floats, we must first align them so that we get the same exponents. You use the exponent of the biggest one. If you have a and b, and we say that the exponent of a is 2 bigger than b, then we have to shift the mantissa. Yeah, we shift the mantissa of b 2 positions right. So we take this. We do the addition over this.
Shouldn't you be rounding in that shift?
And more and more and more. Floating point addition is really complex. Let's look at a ridiculously simple example that proves my point and does nothing else.
Okay.
And also this arrow is not straight. Please don't look at it. Yeah, it's right. So when using BDDs, the variable ordering, the ordering in which you build a BDD, it matters extremely much. So variable ordering makes or breaks BDDs. And when you do addition, you want to interleave them in the order they are actually ordered. So this is the order you want here. A5, nothing. A4, nothing. And then we want A3, B5, A2, B4, etc. So you want a different, you want a different variable ordering depending on the constraint. And using param, we can do this. We can case split on different cases that of the constraints and use a different variable ordering for many of them, and we will end up with something that is way faster. So I hacked together the simplest floating point adder ever. So it can only handle the case where the exponent of a is bigger than the exponent of b. And where is it? Exponent difference, shift b, and then add. So if you just run the full constraint naively, using the same variable order, that is best when the exponent difference is 0. It takes about 26 seconds to run. But if you case split over this difference, you will end up with something that takes 2 seconds.
There are 10 cases or 11 cases, something like that.
Let's see, there are
17
cases.
Oh, okay.
Because this is what I ran. I had 2 hours to make this. Okay. Yes. So splitting over the constraint to use a different variable ordering. This is why param is very powerful.
So how many bits is your exponents? 10 bits, 11 bits.
11 bits.
So you should really be considering exponent differences of up to 2 to the 11.
That's the actual max difference you can have.
Yeah. It's also signed.
So I wonder what the numbers would be, because you would have a lot more cases to consider. And the full constraint is essentially considering all of those.
But if it's bigger than 40, then it's going to be A anyway, because you shift away everything in B.
Yes. Right.
Okay, excellent. So variable ordering, it's really annoying. So can we use set instead? Because one very nice thing about set is you don't have to care about variable ordering at all. But as we said before, set solves a simpler problem. Set returns a single solution, but we need the number of solutions. But however, there are dedicated model counting tools for this. Yes, so for this, we use the Ganak solver. So CNF, you may have heard of, that is the usual input to SAT solvers. And CNF model counters use a modified version of this. So there's no need to specify the variable ordering. and then to conjoin with a constraint, we just add the clauses for the constraint, and then we're done. So here, the idea is this. We symbolically simulate the circuits with AND inverters, which are very cheap data structures to simulate. You can simulate basically everything in under a second. And then for each node, you write out the expression as a CNF file. We call GANAC on this CNF file, and then we load the result, divide by 2 to the n, and then we're done. But we have to make the CNF writer and all this code. So here we have some engineering to do. So first of all, CNF 101. So this is conjunctive normal form. We are looking at a product of sums of Boolean expressions. Each variable d1 is represented as a 1, and its negation is -1. And here's an example of a extremely tiny CNF file, and the interpretation here is the expression on the left. For model counting, we also had to define a projection set. So this is the set of variables that we wish to count over. So here we say that we wish to count over variable 1 and variable 2. Nothing else.
What is the 0?
0 means end of line.
It's a great format.
It's a horrible format.
Yes.
Never be enough for end of line, so I think that.
Don't ask the people who
You
use
just
this.
scanf, and if the number is 0, then you just scanf $D, and then you can parse the whole. It's the simplest parser you can have.
Ask the people who came up with this in the 80s or something. Yeah. So we have this.
Yes, you said that the negation is -1, not 0.
No. So this. Yes. Here. -1. That means not variable 1.
Yes.
-2 is not variable 2, and
Yes, the B is the index of the variable. Okay.
yes. See, that is probably the best way to look at it. Yes. Precise.
Hey, Henrik, I have a question that
Yes.
goes before this when you start talking about stuff. So you did this parameterization, and then but does the model counting still work? Because some of the inputs now are double. Like in your example of A or B, you had 0, 1 occurring twice in your table. Doesn't that mess up your model counting?
Are we talking about BDDs?
Yeah. Just go back a few slides. I thought I was waiting for you to say, aha, but we can't count the models anymore. There. Yeah. 0, 1 now appears twice.
This is where you have to. Wait.
I mean, you gave a talk about this at the NAS-Fabriken meeting, right? Where you were very careful in making everything uniform. Are you ignoring all that now, or?
No, wait. What are we doing?
Or am I just confused? I don't know.
No, but I'm confused.
Maybe we're both confused.
Yes, it works, but wait, why does it work?
You only consider inputs which satisfies the condition, if I remember correctly. I'm not sure how that
You still could
is
join
handled
with
by the
C later
count.
on.
Yes, we're still conjoining.
Okay.
Yes, that's where it works. Yes. So this Friday, I went to the John and Mary workshop, and there was a great talk by some guy called Kuhn or something, and he said, "That's a great question, but my brain cannot handle it right now." My brain cannot handle it.
Something.
Yes. Now, where were we?
So again, so this stuff replaces the stuff you talked about in NAS-Fabriken. Is that correct?
In NAS-Fabriken, we were working on a uniform version of the parametric substitution. So the parametric substitution in itself is uniform. It turns out that's a really bad idea.
Okay.
It's really, really slow because it messes up the variable ordering completely.
Okay.
Maybe it's good for SAT. Who knows? But it's not good for PDDs.
But you're solving the same problem in a different way.
We're hammering the same problem over and over again.
Excellent. Right. Okay. Great if you said that in the beginning. I was waiting for the uniformity is coming. Great. Okay. Continue.
Yes.
Excuse my interruption.
Think this is where we were. Yes. we have our CNF file. We call Ganek on the CNF file, and it returns, yes, there is exactly one solution to this CNF. Excellent. So we have some engineering to do to make this work. So first of all, we need a CNF writer. This is conceptually a quite simple problem, but the implementation itself has a tendency to get extremely messy. Basically, you have to maintain some tables, mapping expressions to variables back and forth, and then you have to use the same table when you load it back. So that's what you have on one screen, and on the other screen, you have the Wikipedia page for the setting transformation. And this is a method for adding extra variables to make the formula grow linearly to circuit size. So this is really what makes SAT work in the first place. And this is actually the reason we need this projection set, because otherwise we would also count over all of these new extra variables, and we get a model count that is way, way too high. Here, for example, is the Satan transformation for an AND gate. So we have A and B coming in, and we introduce a new variable C. And if you look at the CNF file we had before, this is actually exactly the same. And if you remember the answer we got, it was 1, which is good because an AND gate has one solution, which is 1, 1. Great. So now we have written the CNF writer. It's time to test it. So we know that A and B works, but we should probably run a few more examples. So the idea is to, for any Boolean formula f, converting it into a BDD and performing a model count will give us the same result. So of course we're going to use box check again. And no nice GIF this time, but I found bugs immediately. So the first one, it couldn't even handle the constant functions, constant true or constant false. But the solution here is quite simple. You don't even call the solver for those. It's 0 or 2 to the n. And then I discovered I was relying on some undefined behavior. Don't do that. So if you mix references and hash tables in the wrong way, you will garbage collect things you're using currently.
Undefined behavior in what?
In WAS2. I think. Ask Carl, I don't know. These are not things I know too much about. But most importantly, it kept failing at size 4. And after a little bit too much debugging, it turns out this is where the negation starts to matter. And my negation logic, it was wrong. Great. This would be very cool to replicate and show you the error, but I cannot find the old code, unfortunately. So it turns out all of this was a complete waste of time. Because using BDDs is actually way faster. And this is likely due to the memoization. So when we are computing the BDD expression and the signal probability for a single node using BDDs, thanks to memoization, we are doing a bunch of work for the other nodes as well. With Ganak, we don't get that effect because we invoke a new process for every node. So no work is being saved between the nodes. That's not great. So having a better integration here, integration of Ganak into WAS2 would even the playing field, but this is completely out of scope, both for the paper, but definitely for today.
So the reason to not use BDDs was that they explode.
BDDs explode.
Yes. So, and SAT wouldn't explode for those examples, but it didn't solve it anyway, or?
It's just very slow.
I mean, SAT explodes in time and BDDs explode in memory.
Yeah.
So, and then the hope is that you can wait a bit longer, but you can't use a little bit more memory than what you had.
But so you did try on examples where BDDs couldn't be used at all, like where the BDD side.
I just look on fairly small examples, to be honest. But even then, it turns out BDDs are just way faster.
But if you do it for a multiplier, then they should maybe it produce a result.
Oh, yeah, all of the multipliers. Yes, SAT is fast for multipliers, but model counting is not.
Because there are way too many models, or because it's just hard? Because counting is hard.
Because counting is hard, I think. That is multipliers plus counting equals 1, as far as I understand. And unfortunately, I cannot give you a better.
I mean, I don't know about Henrik, but I know that counting models in sub is really, really hard, and it's hard to do anything smart.
Yes to all.
Yeah. Okay.
Yes.
So what I was thinking is like, if you have a multiplier, which is, I don't know, of some size, then BDDs would just crash.
BDDs going to go for lunch. Yes.
Well, because they explode in memory, so you don't have enough memory, so then they wouldn't even finish, right? They would just crash.
Yeah.
So those examples, then would the set solve it, but in a long time?
Yeah. It'd be interesting to have an example like that.
Yeah. Possibly.
But what you're saying is it takes too long, you don't want to wait for it.
Yes. Okay, let's move on. So we go back to BDD-based methods, and the crux here is really how do we deal with this input constraint well. So here we have 3 methods for doing this. In this talk, we have many more in the paper itself. So the first one is naive, as we talked about before. We run it unconstrained, and then we conjoin with a constraint afterwards. Then we can use this identity param, where we constrain the symbolic simulation in itself, and then we do everything as before. And then we have a third method, which is which we realize you can do. You just conjoin all of the input bits with a constraint, and then this will give you the right result. We don't have a proof of this yet, but it's very reasonable.
Only if 0000 is the input that you want, right? Because if it's false, you get 0000. Anyway,
What does it mean you can join all the input bits with a constraint?
So if you run it unconstrained, you put a single variable. That is a BDD with a single variable on each bit.
Yes.
If you instead put, let's say that's the variable v.
Right.
If instead you put the BDD v and constraint on each input bit. Does this make sense?
so if the constraint doesn't hold, that input bit becomes 0. All the inputs become 0. So this is basically the function that I've been saying.
Yes.
If the constraint holds, it's the identity. If it doesn't hold, you get 000 everywhere.
Yeah.
And hopefully 00 is something that you're interested in.
Yes.
So I thought you meant take the conjunction of all the input bits with a constraint. I thought you meant if the input is v1 to vn, take v1 and top.
Then map are missing.
Yeah, it's a map
conjoin.
map
Yes,
constraint. Map conjoin.
Okay, now I understand.
We're all functional programmers here.
Yes. And then we have some more methods. We can also use a general param, but then you need to compute some kind of representative bit to do the same thing as before. And this is a complete headache, but it also works. Another thing you can do is ternary. So the symbolic simulator in BOS2 allows you to also encode error states. So you have a dual rate encoding. If it's 1, 0, it's a 1. If it's 0, 1, it's a 0. But the other two are error states. So you have X or over constraint. And the idea here is to put X everywhere instead of 0, just to see what happens. And then map conjoin all. You basically conjoin every bit with a constraint. Everywhere, let's call it eagerly. And this will actually also give you the right result, as far as I can tell.
I mean, every point in the circuit.
Within the circuit.
It's basically you take every node in the circuit and you AND it with a constraint. Do that. To see if it works.
Yeah, okay. It feels like it should be more expensive than only doing it for the inputs.
Yes, but you don't let it compute a bunch of things to confuse.
Yes.
You always constrain it to the thing you only want. The only thing you want. That's the idea. And of course, we also have the uniform param, which I presented in the previous talks that you talked about. Yes.
So you talk about conjunction.
Yes.
Conjunction is a pretty expensive operation of BDDs because it's so precise.
Mhm.
There are versions of conjunction that are less precise, like constrain and and restrain, and there's many versions that say here's BDD. We're going to simplify it, knowing that this is true. But so then the result will also be smaller than the BDD you started with. When you conjoin something with something, it's it may go up, right? I mean, conjoining something with because conjunction is expensive because it's precise. Have you considered any of those more esoteric operations that are logically ill-defined because they do some algorithms on the BDDs themselves? No. Okay. Maybe that's what you should
give me an email.
Okay, yeah,
please. And the last one is the one I talked about in my previous talks, and it turns out it's not very good because it breaks BDD ordering. So in the paper, we do the evaluation in basically two ways. First is a large scale, just empirical analysis. We take the cross product of, we have a circuit, we have a constraint, and we have a method. And then we run all these configurations to see which method is the best overall. And then for case studies, we will also have some case studies to look a bit closer on a few examples. And for this, we have a single position floating point unit, single and double, and then a maximum of 4 circuits, because this is a method where if you do some trickery with BDDs, BDDs and variable ordering, you can really reduce the problem quite significantly. And then finally, we will have a low power design scenario to really connect back to the motivation. But all of this is ongoing work. So
these floating point units, do they have multiplication in them as well?
Yes.
Okay, and you don't run into this problem with BDDs blow up from.
Of course we will.
Okay.
Then how do we deal with that?
Do you do a similar trick at the case splitting of the, are the
if you split, you will still have a problem.
Okay, I don't know. There's no known good case split for multiplication.
No.
Or is it proved that there is no good one?
This is something Carl knows much better than I.
Okay.
So I will rely on him to make this work.
I see.
Is it possible we have a circuit with some sub-circuits that blow up BDDs? Is it possible maybe to say, well, just ignore that part and produce an approximate result, which gets the other parts right?
Well, in the symbolic simulator, we can just say these nodes that are the inputs to this subpart, just make them all x's. And then you can separately make some approximation for that. But then if you have something, the outputs of this subcircuit, how do we deal with that?
Right, so you could track what was known or if something was within certain
You
values.
would have to guess what the output should be then, in some way.
But in other words, you replace it with another component that approximately does what the other one does, but in a cheaper way, I guess.
You could maybe do that, yes. So for this empirical analysis, I gathered some adders that I have lying around of different sizes, from very small to pretty big. And then we have the ISCAS combinational circuits benchmark suite. And then we have some input constraints. Unconstrained is unconstrained. Mutex says that at most one input bit may be 1. So this is a very tight constraint. And then div by 3, we treat the input as a number, and then that number should be divisible by 3. And then equality, we split the input bits into A and B, and A and B should be equal. No common is that the bitwise of A and B should be 0, so they should have no common bits set. And then overflow says that if we add A and B, it does the addition overflow. So these are the some constraints we came up with.
So why those?
Why we have to pick something, and there isn't a good standard benchmark set. So this is what we came up with.
And
So no things like this used in that and so on. Oh, okay.
I mean,
it'd be interesting to have one that says something like there is a lot of carry.
Yes, we also had one of those constraints for the adders, but not in this talk. We have more constraints in the paper itself. Yes. And then we set a timer. Timeout 10 minutes. We run 3 repetitions per configuration, and we report the median execution time. No need to report the results because the results are all the same because it's exact. And for the results of this tiny subset is in this table, as you can see. So perhaps we will need to summarize what we see here. And it turns out that in this case, it turns out that the naive version is actually best in a lot of cases, in most of the cases actually. But this is for easier configurations. We don't see that big a difference for the easy configurations. But for more complex tasks, as in this table here, the results are highly variable.
So what?
So a dash means timeout. So for this one, none of the methods managed to do it. For this one, the naive version managed to do it, and the other one's timed out. For these two, for example, naive and identity timed out, and conjunction succeeded almost immediately. So it's highly variable, and
It feels as though you need to experiment with longer timeouts.
yeah. But this is what I did for this presentation.
So can I ask you a question? You say easier configurations. What does that mean?
Smaller circuits, easier constraints.
But easier constraints, what does that mean?
An easy constraint has, for example, is very tight, for example.
Smaller number.
Smaller numbers. A very small or a very large number of vectors satisfies the constraint.
I see that. Okay. So it's good to be precise about that, because otherwise there's a danger that you say, well, oh, naive is best in the cases that are easy. And then, oh, look, naive is best in the cases that are easy, but the definition of easy is when naive can solve it. Like, for example, many papers that have test data iteration, they compare it to quick check and they say, well, the easy cases, quick check is best. But those are the easy cases. And then how do they define it? Well, when quick check can do it. And then all the hard cases is where we are best when quick check. And so, right, that's weird if that's. But if you have a sort of a neutral definition of easy, then that makes sense.
I would say it's along the lines of the constraint is very tight, or the constraint is very loose, or the constraint depends on very few of the actual variables, which is what it means to be loose. Something along those.
The size, the BDD of the constraint?
Or the size, yes, that's probably a much better way to put it. Yes,
Yeah.
size of the BDD of the constraint.
What's the leftmost column?
This is the circuit.
I see.
Yes, they have very descriptive names, I know.
How should I interpret that?
And they do not have descriptive names.
Okay.
It's very interesting that
It's one way to process.
Okay.
interesting that the different constraints behave very differently for different circuits.
And I think this is an artifact of variable ordering being a difficult problem to figure out.
So what variable order did you use?
I will come to that.
Okay.
But first, I want to look at this. The multiplier. So C6288 is a multiplier. So simulating with BDDs will lead to exponential blow-up, and the naive version always runs it unconstrained and fails it always, as expected. Whereas if the constraint is very tight for the mutex, the constraint is very easy. They succeed almost immediately. And this equality also succeeds, but it takes a bit longer.
Was that the seconds or?
All of this is in seconds, yes. So variable ordering, it makes or breaks the efficiency of BDDs. So we have a very interesting problem here. So the constraint may have one ordering that it wants to make the BDD as small as possible, but the circuit may have one order that it wants. So how do we deal with this? How do we combine them in a good way to make a good global order? Or do it maybe some other way? So what I did here is offline, I found an order that works well on the unconstrained circuit in a systematic way, I would say. And then online, I set the variable order to the ordering I found offline, I enable the dynamic ordering and compute the constraint. And then I disable the dynamic ordering and run the symbolic simulation. So we get a little bit of both, so to speak. But this is bad for some constraints. So for example, the equality, we really want to interleave the bits of A and B, but I don't do that here. And this may also explain why the naive version was so good, because we tailor the variable ordering after the naive method in a way, the unconstrained symbolic simulation. So future work includes a better comparison with the exact CNF model counters. And for approximation, well, one thing we can look at is approximate model counters. They are getting quite good these days. Magnus Marin recently co-authored a paper about approximate model counters. He proved that it works, as usual. And but if you rely on approximation, is it just best to use Monte Carlo from the beginning?
What does that mean?
If you want signal probabilities, you can just generate 10,000 vectors and compute the signal probability for each of them.
But involve them false because it's so hard to satisfy your.
Well, there are methods for efficiently generating vectors that satisfies a constraint.
But not with uniform randomness.
No, that's the tricky part. This is just speculation.
Okay.
This is just me thinking out loud.
I mean, there's random set, and it's really hard to do random set.
Yeah.
Truly random.
Yeah. And there are also alternative forms of knowledge compilation, which is another term I learned while I was working on this. Knowledge compilation in this context means you have a Boolean formula and you transform it into another representation that makes operations easier. So BDDs make a lot of operations easier, but they are expensive to build. And another of these representations is this format called deterministic negation normal form or something like that. Decomposable deterministic negation normal form. And they are supposed to be quite good for this. So this is a graph-like Boolean formula structure where model counting is easy. BDDs make more operations easy, but they are tailored specifically for model counting. So summary, exact signal probability is useful in many fields, but is computationally hard. We have shown that BDDs are a powerful tool for this, and we have experimented with how to do this well. And maybe the main contribution of our paper here is how do we incorporate this constraint in a good way. I didn't talk about here how to expand this constrained uniform distribution to non-uniform distributions, but you can do that as well in a method in a way that is very useful. And of course, CNF model counters. In this context, I have only seen them being strictly worse than BDDs, but the comparison is really not a fair comparison at this point. And then finally, we have some engineering lessons here. So property-based testing is great. Also, taking the time to write scripts that run a huge number of configurations in parallel, that is also great, because trust me, you do not want to write this by hand. And so, as Kuhn said last Friday, time spent writing code, building infrastructure that quickly tests your work, that is time well spent. Thank you.
I'm wondering about how you might compare with work done by somebody else. Because when I review papers, I always get a little bit worried when all people do is compare with their own stuff.
Yeah. That is not something we can do right now in a way that is fair, I would say. So in a way, I did compare. I have done some preliminary comparisons to this, which is done by someone else, but the comparison isn't really there. A fair comparison is not there.
Yes, you can compare it to. I want to know how much. I mean, it costs to do exact signal probability, but how much do you gain? How much better answers do you get than the approximate answer?
Yeah, that is one. Yes. That's one way to do it. Yeah. Yeah. I guess what to do then is you do some Monte Carlo thing, and then you get the no probabilities for everything, and you find the maximum and make an average
I
error.
mean, there must be standard algorithms for doing approximate.
Yeah.
Signal probability.
Yeah.
That maybe do better than Monte Carlo thing.
Yeah.
And it would also be interesting to what case they use those papers.
Right.
Because somehow adders also, I wonder, are adders good choice? Or are you picking, something easy?
To some extent, absolutely. Yeah. Because it's also because that's what I had lying around, more or less.
I mean, I think the floating point unit thing, that's not, you don't
Yeah.
choose that because it's easy. It's actually, it's going to be hard.
Yeah, we know that's going to be hard.
Yeah.
It's very strange to chair your own session.
Right.
but-
So that's same to speaker.
No.
Oh, he's fine.